Let's solve some math problems involving the antiderivatives and inverse trig functions. The first one is dx over the square root of 15 minus x squared. So if I'm looking at this, I'm going, okay, alright, I'm dealing with inverse trig functions right now, so I know that the sign, the arc sign, is if I have the square root of something squared minus x squared. Okay. But I don't have something squared, I just have this 15. So what I have to do is I have to rewrite this problem so that it looks like the template that I'm trying to use. So instead of 15, what I'm going to do is I'm going to write this as something squared. Well, 15 is the square root of 15 squared, of course, right? It's kind of a, oh yeah. So that tells me that this the square root of 15 squared minus x squared. Okay, that kind of makes sense. So then what you're going to do is say, okay, since I have a squared minus x squared, that tells me that a is the square root of 15, giving me arc sine of x over the square root of 15 plus c. And that's kind of a trivial example, but what you'll find is most of these types of integrals here use that sort of cleverness to try to be able to, they use some sort of simple algebraic manipulation to force it into a template. So the similar situation is here. I go, okay, I see an x out front and then the x squared minus a number. So that tells me that this looks more like an arc secant because the arc sine doesn't have an x out there. Plus, this is something minus x squared, but this is something where it's x squared minus 1. So this tells me, okay, I'm probably dealing with an arc secant case. So in the arc secant case, what I do is I need this to be x squared minus something squared. But I don't have x squared, I have 4x squared. So what I do in this particular case is I factor out the 4. This happens thusly. I say, okay, well that if I pull out a 4 from both terms, I get an x squared, but then I get a minus 1/4. So I get x squared minus 1/4. Now that I've got that, I can pull out that 4, but if I pull it through the square root, I pull out the square root of 4. So that'll get me times 1/2 times x times the square root of x squared minus 1/4. But this 2 isn't part of the template, so I have to pull it out further. So I have to pull it out as a 1/2. But remember, the arc secant template requires that this term also be squared. So I can't just write 1/4, I have to write something squared. So the square root of 1/4 squared. Well, the square root of 1/4 is 1/2. So this is x squared minus 1/2 squared. So now that this is in the template form, I get that that's 1/2 arc secant of 1/2, it would be x over 1/2, which is just 2x plus c. And now moving along, what we're going to do, and this is, sorry, that's not correct. This 1/2 pulls out, but remember the template says that it's 1, so this is a is 1/2, So it's 1/2 over 1/2, because the template is 1 over a, and then we already had this arcsecant of x over a plus c. So the 1/2s cancel, giving us arcsecant of 2x plus c. I apologize for that. That was my mistake. So the next piece here, we have 7 over 81 minus x plus 9 squared. So in this particular case, we can't just use the techniques we have here. We're going to also have to use u substitution. So we don't want x plus 9 squared. What we want is u equals x plus 9. So du equals dx. At that point, this will become a sort of a u squared here. So I'm going to get 7 du over the square root of 81 minus u squared. So the 7 we don't really need. We can pull that out front. And we have 81 minus u squared. Well, our template says that it's got to be something squared here, so we're going to rewrite 81 as 9 squared. So that tells me that my a here is 1. So this looks like this type of problem. It's an arcsine function, or arcsine problem. So in this particular case, it's going to be 7 arcsine u over 9 plus c. But again, we didn't start in u's, we started in x's, so we have to replace this with, replace u with its substituted term, giving us 6 or 7 arcsine x plus 9 over 9 plus c. And that's how you do that type of problem. Finally, we have 3t over a square root of 1 plus 9t to the 4th dt. All right. So I'm gonna change this problem. I'm going to change this problem because we need to see something slightly different. Okay, so we'll rewrite it like this. The reason I'm going to do that is because you're going to see problems like this and you're going to say to yourself, okay, I'm going to solve this with u substitution. So u substitution tells me I should just take that bottom, that whole denominator and take du, right? But if you do that, du is going to be like 36t cubed, which is not very helpful. So what you're going to have to do is be a little more clever about this and say, okay, all right, well, this integral is 3t 1 plus 3t squared squared dt. So 1 plus 3t squared squared dt. And the reason we want to write that is because we're trying to fit this into a box. We're trying to fit it to a template. So if I do that, I can take this piece here as u. I can say, all right, u is 3t squared. Du is 6t dt. So what that tells me is that 1 over 6t du equals dt. Okay? So if I take this and I substitute it back into here, what I get is 3t times 1 over 6t du all over 1 plus u squared. So now I just have 1 plus u squared on the bottom. This will cancel and get me like a 1/2, right? 3 divided by 6, so that's 1/2. And I can pull that 1/2 out, so that leaves me 1/2 du over 1 plus u squared. Okay, well this is the arctangent template. So it's a squared plus u squared, so really this is 1 squared. A squared plus u squared. So that gives me 1/2 arctangent u plus c. Now again, this is u divided by a, but a is 1, and then there should be a 1 over a here, but that again, that a is 1, so we don't have to worry about that. But we started in x's, not in u's, so it's 1/2 tan 3t squared plus c, and I wanted to do that so that we not only got all three, secant, tangent, and sine, and you got to see a lot of different techniques and we're going to do some more problems to really round out this knowledge.